In this video, we're going to look at graphing polar expressions, and we're going to use desmos to look at some of these curves and kind of help us with the classification and the domain and some zeros and all the other things we would use for our analysis. And so we're going to look over here at this first problem, this first polar curve of r equals 2 minus 2 cosine of theta. And now when you go to graph it in desmos, what you would need to do is turn on your polar grid, and it's its own, instead of the rectangular grid here, it has its own grid, which gives us our polar graph. And we want to make sure we're in radians because that's what our graph is that we would eventually sketch it on, would be in. And then we would type in our equation r equals 2 minus 2 cosine of theta, and it puts the graph up there. And first thing we want to do is we want to try to classify what this curve is. Now, this curve is a type of Lemezon curve. In fact, it's a cardioid. So you classify it as a cardioid. And the reason why it's that is because these kinds of graphs will have a distinct bump in it that kind of looks almost like an apple, maybe, where it kind of comes in and touches. It doesn't make a loop, but it comes in a distinct point, in this case right there at the pole. And then now we want to look at, well, what would the domain be to create the full graph? And you can actually, this is a little bit of trial and error per se when you're first starting off looking at the graphs is, well, what would my interval be for theta to produce that entire graph? And I could just start and say, all right, well, let's go from 0 to pi. And I look from 0 to pi, it only made the top half of this graph here, and say, okay, well, I'd keep adding to that and say, what about 3 pi over 2? Nope, that's not quite it either. And we look at 2 pi, and 2 pi makes the full curve. Now, I could also ask myself and look and say, well, there's got to be a way to do that without trial and error on the graph. And there is. I look at the cosine function itself. The period of cosine, in order for it to produce all of its possible values in terms of the cosine wave, is 2 pi radians. And so start to finish, we are going to go from 0 to 2 pi. So that's the way I could tell. We go from 0 to 2 pi. It's going to make the full graph. So 0 to 2 pi. And in fact, I could exclude the 2 pi because it's going to be the same point as 0. Now, define my zeros. Now, technically, the zeros in this case are going to be when r is equal to 0. So when does r equal 0 on this graph? So when does it intersect through the pole? And I would, by hand, I would make r equal to 0, and I would go solve for theta. And I could look at that expression and say, all right, well, that right-hand side is going to produce 0 when cosine equals 1. And then I would solve for theta. Well, cosine is going to equal 1 in terms of my unit circle at 0 and at 2 pi radians. So I could say the zeros here are going to be at 0 and or 2 pi radians. And the maximum R values and when they occur. Well, graphically, and I look over here at the right-hand side, the maximum R value is going to be when is the graph its farthest away from the pole. Well, I look at the graph, and it is farthest away from the pole when it's way over here on the left-hand side, which is at pi radians. Now, how would I know that by doing it by hand? Well, I would try to figure out, well, the maximum R value, and for our equation here, the biggest value that's going to produce is 4. So the maximum R is going to equal 4. It's going to be when I add whatever the largest value is for cosine to the 2. Well, the biggest value that cosine can output is going to be a 1. And in fact, I need to be negative 1 because negative 1 and negative 2, add that to 2, that make 4. And so once I identify what the maximum R value is, I would set that equal here and say, all right, so 2 minus 2 cosine of theta, and I would go solve for theta, and that's going to be when cosine produces a value of negative 1. Well, cosine produces a value of negative 1, at pi radians. So when theta is equal to pi. So by hand, that's how I would do that. And we'll classify the symmetry where you look over on the right-hand side here, and it is symmetric of what would be considered the x-axis, but in terms of polar graphs, we'll say that it's symmetric about the polar axis. And we could create a sketch down here on the bottom. Now there's one other thing that I want to show here on this video is, well, because Desmos doesn't let you trace or click on a curve, but I could trace around and try to see, well, where is it plotting at for certain values of theta here? And the process is kind of simple once you do it once or twice. And what I want to do is I want to copy this function that we've already typed in. So I'd click the gear, I'd click copy, and it's going to bring it down right here beside it. And I'm going to change the color of it. So I'm going to click the dot, and I'm going to make it be dotted, and let's go purple. All right, so it's going to make a purple graph. And what I'm going to do is, over here beside it, is I'm going to create a domain interval for which it's going to plot. And so I'd have to get my set bracket here, and we're going to go from 0 less than or equal to theta, and I don't have a theta button, so I have to type it in, and all the way to 2 pi, okay? And actually, not to 2 pi. What we're going to do is we're going to go to some constant, call it a. So that way, when I put a in, it says, do you want to add a slider? Yes, I do. And I'm going to set my slider for a to go from 0 to 2 pi. And I'm not worried about the step per se. And so what will happen is, as I drag this slider, so as I drag the slider for A, it is going to start plotting around the curve here, which is kind of neat. I can see the direction it's traveling if I was over here plotting it, and to help me make some of these curves. And in fact, if your domain was too big, you could see when or how to shrink your domain down to make one full graph here. Okay, so I'm going to go ahead and I'm going to plot this on my curve on the graph, and then we'll be all done with this problem. And we have a sketch and a pretty basic analysis for this particular polar curve. All right, let's look at another one here. This time, let's look at the graph of the polar curve r equals 2 plus 4 sine of theta. And let's perform an analysis. And so I already have them typed in here over on the right-hand side in Desmos, where I have the curve r equals 4 sine of theta. And then I use the trick that we talked about in the previous problem, where I'll set a domain for theta on a second curve and change the color. Well, we'll go from 0 to 2 pi as well. And we can use this slider of A. Now, this curve itself is a type of it is a Lemaisan curve. And it's a Lemaisan curve with an inner loop. So, Lemaisan with an inner loop. And we try to figure out, well, what is the domain for the full graph? And I can discover that with the slider, where we try to start at 0 and see how long does it take for the function to completely map itself and do everything it's going to do. And so I'm dragging my slider, looking at its tracing, and by the time I get all the way to 2 pi, it's all the way, and it did everything it's going to do, and it's back to where it started. So the full domain for this graph, we can say, is from 0 to 2 pi. And let's go and let's start talking about, well, where are the zeros? Zeros in context of a polar curve is going to be when r equals 0. So let me zoom in. So the zeros are going to be when r is equal to 0. And so I'd set my equation equal to 0, and I'd go solve for theta. Well, this expression is, the r is going to equal 0 when sine of theta is equal to negative 1/2. And then I use some unit circle intuition to figure out, well, where does sine equal negative 1/2 at on my unit circle? And inside of that domain we have from 0 to 2 pi. Well, it equals it at 7 pi over 6 and 11 pi over 6. Now, what's interesting about that is, well, we can now, if we wanted to, we can determine the domain for the inner and the outer loops. And so let's look at we'll play with this, our slider here to try to figure this part out. And in fact, let's look at going from, see what happens from 7 pi over 6 to 11 pi over 6 to see what we can do in between here. Now, 7 pi over 6, so it's already plotted some of that curve there for me. And in fact, let me change the trace function here to go from 7 pi over 6 to 11 pi over 6. All right, and if I trace inside of there, that in between those two numbers is my inner loop. So we could say the domain for the inner loop goes from 7 pi over 6 to 11 pi over 6. And the outer loop is going to be everything else between that, our domain interval, excluding that. So we could say outer loop is going to be from 0 to 7 pi over 6. And whether or not we include or exclude that number is irrelevant because it's at the pole. So I'm going to include it and go from 11 pi over 6 to 2 pi. All right, maximum R values and the theta values where they happen. Well, I'm looking at this polar graph, and it looks like it goes all the way to a radial value of 6. R is equal to 6. And if I go back and look at my equation, well, I can make R equal 6 if sine produces a value of 1. Because if I subtracted the 2 over divided by 4, I got 1 is equal to sine of theta. And sine equals 1 on my unit circle when theta is equal to pi over 2. All right, so pi over 2 is going to be when we have our max. And lastly, for our analysis would be the type of symmetry that occurs in this graph. Well, the type of symmetry would, if it was the xy plane, it'd be symmetric about the y-axis. Well, these axes here are not x and y axes. So we'll actually say the vertical axis on this polar grid will be the line theta equals pi over 2. Is where it's symmetric about. And we would just from here copy our graph onto here, and we would have our sketch along with an analysis. And there's our sketch of this Lemaisin curve. Okay, let's look at this next one. R equals 6 times sine of 2 times theta. And I already have it put in here on desmos, and we look, and it makes a rose curve. I see all the different petals. So we have a rose curve. It has 4 petals. We don't have to write that. Now, the domain for the full graph. And if we're looking, some people will look at this and say, all right, well, wait a minute now. Can I just look at sine of 2 theta and say, all right, let's find what the period is for sine? Well, the period of sine would be 2 pi. And if I multiply theta by 2, that means this period should be pi radians. So if I make my graph here to go from 0 to pi, see if it makes the full thing. It doesn't. It only made half of it. And so sometimes that logic in terms of, all right, well, how long will it take by going off our trig functions can be slightly flawed because the way this graph works, we have to account not only for the sine value, but our theta values that correspond to these as well. And the graph here is to go from 0 to 2 pi radians to make the full picture. And so our full picture here is from a domain that goes from 0 to 2 pi for theta. And let's try to go through and I'll say, all right, well, what's next? Let's find the zeros. When does R equal 0 on this graph? So when does it intersect the pole? Well, I've set my equation equal to 0. and I solve for theta, well, that's going to equal 0 when sine of 2 theta produces a value of 0. And we have to think, all right, well, sine of what values? This is where we go into our unit circle. Sine has to be applied to whole pi's to equal 0. So I start working my way around the unit circle, but I'm also having to multiply these values by 2 as I do it. So the first place it would equal 0 would be 0 itself, because sine of 0 is 0. And the next one would be pi radians, but in fact, because I'm doubling theta, pi over 2 would be another place where it intersects the pole. And then we're working our way around and say, all right, well, pi radians would work, because pi times 2 is 2 pi. And the next one would be 3 pi over 2. Because 3 pi over 2 times 2 is 3 pi, and that would make sine equal to 0. And so there are 4 intersections of the pole as we're working our way around this graph. And so let's kind of trace through here, and I already made the slider, and let's trace this function as we go from 0 to 2 pi and watch what's happening. All right, so I'm looking here. It starts off at 0. And as I work my way around, it goes through the intersection again, and then another time, and then another time, and then another time. All right, so it goes through the pole 4 separate times. Now, we could ask, well, what is the interval, or how big is the interval for one of these flower petals? Well, we kind of already done that by finding the zeros themselves, because we start at 0, and we go from 0 to pi over 2 are my first 2 intersections of the pole, and that first petal is created. So the first petal, or one petal, if someone were to ask, could be graphed to go from 0 to pi over 2. And then the next one would go from pi over 2 to pi, and pi to 3 pi over 2, and then 3 pi over 2 to 2 pi. Now let's look at our maximum R values. Well, this is where we're looking for, where is the absolute value of R going to equal, well, how far away do these petals get on this polar grid? I'm looking at how far away do they get from the origin. They make it all the way to that circle with the radius of 6. Well, when I'm looking at my equation here, I should know that, because I'm multiplying sine's output by 6, and sine itself has the largest output is 1. 1 times 6 is 6. So I'm going to have this values so I'm put 6, and I say, all right, when will 6 times sine of 2 theta equal positive or negative 6? Well, we're essentially asking ourselves, when does sine of 2 theta produce values of 1 and negative 1? And so we go back to our unit circle knowledge here and come up with values of theta around our unit circle. Well, sine will produce values of 1 or negative 1 at pi over 2 or 3 pi over 2. But we have to keep in mind that we're doubling the values of theta, so we're going to have more than just 2. So I'm looking here and say, all right, well, when is the first theta value that I can make sine be applied to pi over 2? Well, since I'm doubling, the first one would be at pi over 4. Pi over 4 times 2 makes pi over 2. And then I'm working my way around and say, well, I could also cheat and look at the graph, and I see the next extension of that petal is at 3 pi over 4. Well, because 3 pi over 4 times 2 is 3 pi over 2. And then I keep going and say, all right, well, the next petal looks like it's at 5 pi over 4, and then 7 pi over 4, are all the max when the polar curve is its maximum distance away from the pole. And our symmetry here, well, this graph here, now we look at our symmetry in terms of being symmetric about the polar axis, the vertical axis, and you could even say the origin when technically it's the pole. I could fold these petals, this rose curve, it's symmetric about the polar axis. I could fold it along the horizontal and lay on itself. I could fold it over the vertical axis, which is the line theta equals pi over 2, and it would lay on itself. And I could even fold it over both the line y equals 2 and the polar axis, and it would lay on itself. And I would just call that the origin. Okay, and then we would just create our sketch of what is happening here on our little graph here below. And we know it's going to intersect that pole multiple times, and it has its maximum r values at all the pi over 4s, which is when it equals 6. Okay, let's look at one more polar graph here, and this is the graph of r squared equals 49 times cosine of 2 theta. And one of the first things we're going to notice is whether if you're trying to type it in on your calculator or desmos. Desmos does not allow you to type in polar equations as r squared equals. It would just wants this r. And so I rewrite this as r equals the square root of 49 times cosine of 2 times theta. And in fact, that is going to make the same graph as if I typed it implicitly with r squared. And so it's already typed in here. This is a lemniscate curve. And we want to find what the domain is for the full graph. Now, one thing you'll notice is if you pay close attention to the graph over here on the right-hand side, and I'm tracing this slider. And it would appear, if I did it really quickly, that from 0 to 2 pi, it would make the whole thing. However, if on close inspection, there's actually a pause in it plotting the point. So like I work here and it hits that pole for the first time, and then I keep going to the right, and it's not plotting any points for a little while. And then it starts back. And then it does the left-hand side. And then it hits the pole, and then it stops graphing for a little while. And then it picks back up. And so it makes me wonder, well, what is actually going on? Why is it not plotting points in those specific places? Well, before we get into our domain, and something that's going to help us is, let's start by trying to find the zeros of this. So we try to figure out where is it that r is going to equal 0. Well, r is going to equal 0 on this graph when cosine of 2 times theta is equal to 0. And we go to our unit circle and we think, all right, well, what theta values will cosine equal 0 at when I double them? And we're going to generate a list here of pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, and I'm excluding 2 pi because that's the same point as 0. Well, 2 pi is technically not 1, but when it comes to making our intervals, I'm going to exclude that. Now, so that's everywhere that this graph is crossing the pole. Now, here's the thing to keep in mind, is actually with the way we have this curve typed in desmos as r is equal to the square root of 49 cosine of 2 times theta, we know that it's possible for cosine to produce negative values. And if I take the square root of a negative number, it's non-real. So what's happening is everywhere that cosine produces a negative value, it's not plotting points. So now we have to go through and let's look and figure out, well, on the intervals, from 0 to 2 pi, and we have all these other these places on our from start to finish where we're producing values of 0. It intersects the pole. I'm going to do a sine test here and figure out, okay, well, where is cosine producing positive numbers, or cosine of 2 theta producing positive numbers, and where is it producing negative numbers? So that way I can make this domain. And we can use our slider a little bit to help us. Initially, it's plotting points until I get to 0 for the first time. So between 0 and pi over 4, cosine of 2 theta is positive. I just think about that for a second. That's really, when I'm doubling these values, I'm going from 0 to pi over 2. And then when I go from pi over 2 to pi on my unit circle, In fact, from pi over 2 to 3 pi over 2 in my unit circle, cosine has negative values, and which is going to be the interval in this case from pi over 4 to 3 pi over 4. It's producing negative numbers. And so that first blip where we're not plotting anything is that interval from pi over 4 to 3 pi over 4. And then we start back. Well, 3 pi over 4 to 5 pi over 4, if I double those, is really from 3 pi over 2 to 5 pi over 2, which is the right-hand side of our unit circle. So it's all positive there. And that's going to be when it's plotting this left part of this loop here inside of there. And then it stops. So this is between 5 pi over 4 and 7 pi over 4 everywhere it's negative. And then it'll plot the last little bit here in this interval where it produces positive values again. And so our domain, we're going from 0 to 2 pi, but actually the domain interval that we're looking at is going to be broken up into pieces because we're going to have some values where technically the graph is non-existent. So we could go from, we'll say from 0 to pi over 4, and then from 3 pi over 4 to 5 pi over 4. And then 7 pi over 4 to 2 pi. Okay, now let's go back to figure out, well, what are the maximum values of R? Well, if I'm looking at this graph, the maximum values of R are, it's at on the curve when R is equal to 7. So the max R value, in this case, or an absolute value, is going to be 7. And I want to figure out, well, when or where does that happen on this curve here? When is it actually equaling those numbers? Well, we are looking, in this case, for when cosine of 2 theta on our graph here, which we have the square root of it here, is equal to 1. And that is happening. Where does cosine equal 1 at? Well, cosine equals 1 when it's applied to 0 and pi, or excuse me, 0 and 2 pi. But we're doubling, so we have to think about, all right, so I'm doubling these theta values. So definitely theta would work. And then it'd say, all right, well, what about pi over 2? If I put pi over 2 and I double that, that's going to give me pi, but it'd make me take the square root of, I'd have negative 1, so I'd skip the pi over 2, and we go, the next time it actually would equal positive 1 now, because I can't use negative 1 because it'd make me take the square root of the negative number the way it's typed in. Theta equals, cosine will equal positive 1 when it's applied to 0 or 2 pi or 4 pi and so on. So I'm looking for these theta values that when double will make cosine be applied to those. 0 would work, and so would pi, and there's no other theta value that would lie inside of the intervals that we have written up here. And last thing we have for our analysis is talk about symmetry, where I'm looking at this curve here. It is symmetric over the polar axis. It is symmetric over the vertical line, theta equals pi over 2. And it's also symmetric if I fold it over both of them. We'll call that origin. Symmetry or the pole. And we would just from here, to make a rough sketch that goes with this, is to plot the curve on the grid here below. And we have our sketch and our analysis.